Another approach to the image segmentation problem is to represent the image as a graph. And then segmentation essentially is finding cuts in this graph. So let's take a look at how we represent an image as a graph. So here's an image, and we can simply say that every pixel in the image is a vertex, and we have an edge between pairs of pixels. Perhaps not all pairs of pixels, just the pairs of pixels that are close to each other. So then the notation is that we have a graph G with vertices V and edges E. And each edge has a weight associated with it. So each edge is weighted by the affinity or similarity between its two vertices or pixels. So this notion of affinity is very important to the way this segmentation actually works. And so let's take a look at the concept of affinity. So let's say that you have pixels I and j, and there's an edge between them, and its features are fi and fj. So we can say that the dissimilarity between these two pixels is s. We've seen this before, the L2 norm between the two features fi and fj. Now using s, we can define the affinity. So the affinity is a between feature fi and fj, which can be defined as e to the power of minus 1 over 2 sigma squared s. So the smaller the dissimilarity s, the larger the affinity. And this relationship is defined by the parameter sigma right here. So this affinity is the weight associated with the edge, wij. Okay, so now let's define what we mean by a cut. So here's a graph, and a cut C is a partition of the vertices V of a graph G into two disjoint subsets VA and VB. And the cut set are essentially the set of edges whose vertices are in different subsets of the partition. So this is the cut, and these edges correspond to the cut set. And finally, we have the cost of a cut. So the cost of the cut is simply defined as the sum of the weights of the cut set edges. That is all of these edges right here. Okay, so with this in place, we can develop our algorithm. And our algorithm essentially uses the following criteria. The first is that a pair of vertices within a subgraph should have high affinity. That makes sense. That's like similarity of pixels. A pair of vertices from two different subgraphs should have low affinity. And finally, we want to basically come up with cuts that have minimum cost associated with them. So that's also called min cut. So that's our goal here. So each subgraph that we end up with at the end of the day, so let's say that we're showing this as a caricature here. This is one subgraph, another subgraph, and a third one here. Each subgraph is an image segment. That's a result of the segmentation. All right, so that's very simple, but there is a problem with the min-cut algorithm. The problem is that there is a bias to cut small isolated segments. That is, in this particular case, let's say that these are pretty weak edges with low affinity right here. And so you would like to have this as your desired cut. But the cost of cutting all of these three edges happens to be greater than the cost of cutting this single edge, even though it has pretty high affinity right here. And in fact, it's even greater than cutting these two edges right here. So this is the lowest cost, this is the second lowest, and then you have this one right here. So what this goes to say is that you somehow have to normalize a cut such that you favor larger subgraphs. Otherwise, you're going to end up with lots of tiny little fragments that get chopped off just because they have low cost. You need to normalize with respect to the size of the subgraphs. So that requires us to come up with a measure of the size of a subgraph. And one way to do that is by seeing how strongly the vertices of the subgraph VA are associated with the larger graph V. And so we call that the association between VA and V, and that's just the sum of the weights between the subgraph and the larger graph. So in this case, if you're looking at this to be VA, then that would be just the weight of this edge right here. In this case, if you're going to cut right here, the association is much greater because it would include all of these edges which belong to VA but are a part of V as well. So association is the sum of the weights of the solid edges shown here in these two cases. This is weak association and this is strong association. So you want to use this concept and somehow take our cost of the cut and normalize it with respect to association. So that brings us to this notion of normalized cuts, N-cut. So we want to minimize the cost of normalized cut during partition, where N-cut between VA and VB, if those are the two subgraphs that we're going to end up with, is the cut, the cost of the cut into VA and VB divided by the association of VA with V plus cut VA VB divided by the association of VB with V. So that's the algorithm, and the one issue here is that there is no known polynomial time algorithm for solving this. It's an NP-complete problem, but there are many approximations that have been suggested. And one of the popular approximations was suggested by Xi, which uses fast eigenvector-based approximations. These are called spectral methods, and they were very widely adopted for segmentation problems. So here are some examples of segmentations. By the way, the feature here includes both the brightness as well as the location XY. These are the segmentation results. And these are very complex images, as you can see, and these are reasonably good segmentations given the complexity of the images. So with that, let's summarize what we have covered in terms of image segmentation. First, segmentation is naturally a very important problem in computer vision. It's used as a precursor for object detection, object recognition, and so on, classification as well. And the first method we looked at, the simplest of them all, is k-means segmentation. And then, as an improvement to k-means, we looked at the mean shift algorithm. And finally, we looked at normalized graft-cut segmentation. And I should mention that what I've described here are the most basic versions of the algorithms, and particularly when it comes to mean shift and graph-based algorithms, there have been many improvements that have been suggested, which you can find in the literature.